Thank you very much. Hello, everyone. Gephi doesn't exist in the web world in JavaScript, right? But what if it existed in this different world? Let us present ourselves. So I'm Mathieu Jacobi. I'm the original author of Gephi, and I'm a researcher. And Eduardo here is the lead developer of Gephi since quite recently. And if you know Gephi a little, he has been developing the data laboratory view, right, among other things. And we've teamed up with JavaScript experts that know very well the web world for network visualizations. Alexis Jacobi, who is also my brother, and Guillaume, Guillaume Plic, who is in the room. So they've helped us see what it would look like, right, if you want. But I need to talk about the context on why we are in this situation right now. So basically, the multi-platform is moving from Java to web technology, right? So the browser is now the new multi-platform, if you prefer. And this is an effect, for instance, of multiple factors, but one of them is the policies of Oracle, right? So they want Java to be more a back-end thing and less a front-end things. So there are less and less user interface features in Java, they are less maintained, and we are kind of stuck in this general movement, right? And for instance, a very technical, very practical consequence for Gephi is that the library, the OpenGL library we currently use is not maintained anymore, right? And it will not be better in the future because of the general movement, right, of having less UI stuff in Java generally. So at the same time, the JavaScript is more powerful, right? We have crazy efficient applications now. It's more mature than what it was before. We are switching from a web of documents to a web of applications. So should we consider moving Gephi from the Java world to the web world, right? In this talk that we will split in different parts, we will see first how to fix Gephi and how to deal with these issues of deprecation of OpenGL libraries in Java currently. And basically, Eduardo redeveloped a new OpenGL engine for Gephi. And then into the JS world, what would we have to do to transition to JS, what it takes, what it costs, and what we would gain. And Alexis will present that. And then we have a small benchmark that shows if JavaScript can really be as efficient as Java for graph visualizations. And without further ado, I'm going to pass the mic to Eduardo.
Thank you. So before talking about JavaScript, we will first stay in the Java world. And I want to present you some problems that we found over the years with the heart of Gephi, which is the rendering engine. And there are a few problems. First, it uses deprecated OpenGL functions, very, very old. So they don't even work in some older or incomplete drivers and can crash many computers, especially on Linux and OS X. Also, it has a problem of scale. It cannot scale with the modern GPUs that you can buy nowadays because it has a lot of CPU overhead, and that's because of calling a lot of functions of OpenGL on the CPU, which is just too much calls every frame of the rendering. And also, we have listened to our users, and they want to use a Gephi rendering engine as a library. They would like to have it on their own programs, but that's not possible at all because it's not modular and it's not clean, and it's just not portable. And also, at the same time, we are going to improve all of this. We also want it to be extensible with plugins, so it's not just what it is, but it can be changed by any developer. And of course, we can improve it. So before creating a new engine, I found very few difficult choices to make, mainly two. One is choose a Java library for dealing with OpenGL in Java. So Gephi, since always has been using the GeoGL library, but the problem with it is that it's not maintained anymore. We also want to thank the GeoGL developers for the work during the years, very awesome work, but nowadays we have to make the switch to another library, and that's the lightweight gaming Java library. And it's great. It's great. It works very well. It has many functionality, but it has a small problem, and it's that it doesn't officially support a solution for building a graphic user interface, which for Gephi, as you saw before, is a deal breaker, because we don't want to build a game. We want to build a desktop application or web that integrates a graph, but the graph is not everything. And also, last year we found that the future for OpenGL in Java or the desktop is kind of uncertain. That's because first, Vulkan is supposed to be the successor of OpenGL, but still is unsupported by older drivers, older GPUs, or older systems. And at the same time, Apple decided to deprecate OpenGL in OS X, and they also said they won't support Vulkan, which makes them the only ones not doing it. And it seems they are trying to enforce Metal, which is their own graphics API, which is only for OS X and iOS. But is that too bad? I don't think so. OpenGL still works in OS X. It will continue to work. And also, there are starting to appear solutions to fix this problem in the future. So you can write OpenGL programs that work on top of Metal. So it should continue working for the future. And also, there's software being created in OpenGL nowadays. So I don't think we should move that. So now I will talk about the new engine that I have been developing to completely replace the current engine of Gephi. So you will see that it looks exactly the same, but fixes a few known glitches, old glitches. It's also written from scratch, only depending on the graph API, the core graph. So that should make it very easy to integrate both in Gephi and other applications. Also, it offers extension mechanisms, so you can plug in some components to draw anything, for example, a background map or a legend, whatever. And you can also extend the input, so you can write plugins to deal with the user interaction, for example. And also, I wanted to make it work with older versions of OpenGL, which some older machines might support, but not the new shiny things of OpenGL 4, for example. So this engine tries to use whichever functionality is available, going from best to older, which affects performance. But if the new version of OpenGL is available, it should work really fast and much better than nowadays. And the other aspect of designing this new engine is that it changes from the fixed pipeline of OpenGL to the shader-based modern OpenGL, which makes it easier to write some plugins to render anything. And also it tries to be high performance by following the approaching zero driver overhead design principles, which in summary means that you do all the data preparation work on the CPU in a buffer, in a low-level buffer. You don't call OpenGL functions at all. And when you have all the data ready, you call the OpenGL function once to tell it to draw everything in a single batch or two batches or whatever. So that makes Gephi use correctly the powerful GPUs that nowadays are available. And also the geometry of nodes and edges. Before it was being repeated and sent again and again. Now we have one instance of the node geometry and we transform it on the shaders. So that saves memory for the graphics card and that saves data interchange. And about the previous problem that I talked about GeoGL or the lightweight Java gradient library, I think the correct choice is this one. First, because it's maintained nowadays. It also offers bookend support, so in the future, if we need it, we just can use it. But the IWT problem, what can we do to build a user interface? Well, there is one small project in GitHub, unofficial, that offers that. It works quite well, only for Windows and Linux at the moment, but we would like to implement it for OS X too and make it better and contribute that. And let's do a small demo. Okay, so we close Gephi with the same graph, and we are using the new engine. We are using it with a very simple card, which is the integrated Intel card. It works much better if you use a powerful card. But as you can see, this is a window that is completely out of Gephi, so you can use it in your own programs. It's also tested on different drivers. For example, Gephi currently crashes on my Linux installation, but this engine doesn't crash and will work fine. And this is a smaller graph, but we have seen it work with millions and millions of edges, which is not possible with current Gephi, and Matthew will tell us about that later. So now, thanks for Alexei.
Thank you. So now that we've seen the whole part about how fixing Gephi in the Java world, I'm going to try to explore what it could make possible or impossible to write Gephi for the web. First, I think the most important thing is to describe what I think is challenging is in writing Gephi. I've been using it years ago, and I think there's three main qualities of Gephi. The first thing is that it must be able to render hundreds of thousands of items or millions of items really smoothly, like as often as possible, if possible, like 30 times per second, without freezing the whole computer or even just the software itself. Also, it needs to have a performant graph model. We need to be able to, at the same time that we're drawing this whole graph 30 times per second, compute like community detection algorithms or ranking algorithms, all of this still smoothly and without freezing the whole computer or the software itself. And finally, one of the main qualities of Gephi is its plugin capabilities. You have to be able, if for your needs, your business needs to implement a specific ranking algorithm or something, to integrate it inside Gephi without having to rebuild the whole thing. Also, this allows like the current marketplace of Gephi. You can download a lot of different features that make Gephi your own Gephi and that makes it solve your business needs. So those three things are, I think, the three main challenges. About web development, there is some obvious trade-off when you come from the Java world going to the JavaScript world. Let's see it like this. First, most web technologies have been mainly designed for writing interfaces. So this whole block management, styling, forms, inputs, this is so easy in the web. This is made for it. I don't know exactly how it is in Java, but I think it's okay. Thank you. And also, if we successfully bring Gephi to the web, We will still have it work in every OS and also on mobiles. I don't see data scientists working on Gephi on mobile right now, but this is quite imaginable. But tablets, I can imagine a lot of people want to work with Gephi on tablets, and minority report effect to move the graph with your fingers, things like this. This will become possible if we move to the web, and without any effort. But at the same time, there's big losses that we will meet instantly. Memory kind of doesn't exist in JavaScript. We never know how much memory we are using. We do not know how much memory we can use. And this boundary is actually unpredictable. It depends of the user's computer, his browser, if the browser has other tabs opened, etc. So we know at some point it might crash and make the whole thing stop working, but we never know when. This is quite uncomfortable to work with. Also, we do not have multi-threading in the web. I'll speak about it later, but we do not have very much usable multi-threading. And finally, one minor point that is not written here, I will not speak about Canvas and HZG, etc., because this is all CPU-based and this doesn't scale, so we will already accept that if Gephi moves to the web, it's going to be with WebGL. But WebGL, which is our best solution, is just a subset of OpenGL. It's based on the OpenGL ES specifications, that is a portable OpenGL, and it lacks some features of it, and other features are actually badly implemented, so that's something we will have to work with. So let's talk about web performances. I think one way to synthesize all the researches and improvements that have been brought to this community in the last few years, there's a lot of people who've been working to make the web more performant by improving the JavaScript engines themselves. And I think the most famous success of this part of this field is V8 from Chrome. It's maybe one of, if not the best interpreted language engine that we have now. You can write JavaScript like without caring about performances, and V8 will make it like perfect. That's very, very nice. And on the other hand, there's people who are trying to make the web a performant platform to allow people to actually run bytecode in it. So you will develop low-level applications with C++ or Rust and compile it and put it in a browser, and the browser becomes kind of a new JVM or something that will make people able to just run fast code in it. But it's no more JavaScript. So the JavaScript part, let's say it's all the web development that is modern now, like React application, Angular, all those frameworks, and ECMA 6, ECMA 7, the new debugging tools, all this part that is what I think is web development today. It's really great because, as I said, you can just write any kind of JavaScript and it will be fast. But we have kind of a specific use case here. Writing thousands of DOM nodes and having run smoothly is something. Drawing millions of items is really different. So I think all this web development ecosystem doesn't actually solve all our issues. And on the other hand, writing low-level code and running it in the browser as if it was a virtual machine only is not webby. I'm a web developer and I want to keep beneficiate from all those nice things, the debuggers, the new specifications of JavaScript that are brought every year, etc. So what I don't like in this part is that it's no more web development. We were writing in the slides, no, not in the web culture, so many times that we just created a label for it. That's going to make it easier to identify. So to wrap up this part, we don't have the same needs as classic web apps. WebGL is the best we have, and we want, if we move to the web, to create something that is webby. We want to beneficiate from all those nice things that have been brought in web development these last few years. Now, Guillaume and I have been developing Sigma.js for some years, and we have some feedbacks about what is doable and what is hard, and about writing a web-based graph visualization library. So first, let's speak about a bit about WebGL. For a web developer, working with WebGL means working with low-level data structures, which is not very in the web culture. To say quickly, you work with byte arrays, that's nice, but you don't have the APIs to actually do what you want. You cannot allocate or unallocate memory as you want because this is not JavaScript. This is not what JavaScript does. And so this is kind of painful to work with WebGL for a web developer. Also, rendering efficiently custom shapes is hard. I mean, the first time I started working with WebGL, I spent more than a week to just draw a plain disk, and another week to draw a plain disk in front of another disk. That was kind of awful, and it requires lots of tweaks on every side. And Guillaume has been working just to draw curves efficiently, and he could speak 2 hours about it, and this is quite painful. Also, it is not 100% stable. If you work with WebGL, you have to accept that at some point it will break and stop working, and you will not find out why. And also, you will see a lot of weird artifacts, really a lot of them. Okay, but it's the best we have. About the graph model, we have kind of a dilemma here, because working with efficient, dynamic JavaScript structures, such as objects and arrays, etc., is really nice, because the APIs are nice, and it's all fast, because V8 is awesome, but it takes a lot of space in RAM. It takes so much space in RAM that we expect that at some point we might cross this imaginary boundary that we cannot identify. So this is not our solution. We cannot base our whole graph model on these data structures with all the indices we want, because at some point this is going to be the issue. And at the same time, we could work with byte arrays, but it's not in the web culture still. There's a lot of things that are very hard to do, and the code will be hard to maintain and hard to test. So we think the best solution would be to have a hybrid solution, but still, this is going to be something challenging. And finally, I want to speak a bit about threading. So we have no multi-threading in JavaScript, but this is how it works. You open a web page, and you have one thread that will be shared between the JavaScript engine. So as long as you have JavaScript running, nothing else runs in the thread, and the rendering engine. So this is called the event loop. If you have a synchronous task running into the main thread, the event loop will be blocked, and you won't be able to scroll the page or hover simple buttons elements of this kind of things. But first of all, if we stop working with Canvas and SVG or DOM and we start working with WebGL, the rendering will not freeze the event loop. This is kind of the good thing. Even if the GPU takes time to render the image, the event loop will still be properly running. And finally, we have web workers that allow us to actually run heavy computations aside from the main thread, so without blocking the event loop. But you have to share your data and actually transfer it. So as long as the web worker is working with your low-level structures, you cannot access it anymore from the JavaScript main thread, which is very weird. It's like all your references are broken, and you cannot do anything. So you cannot render it anymore. We know that there's a new API that's named Offline Canvas API that might allow us to actually trigger rendering from the web worker. So we might have actually the whole rendering and computation engine working on the web worker and keep the event loop running smoothly and safe. So it's actually not that bad. We might be able to do something working nice. So how to actually move Gephi to the web? We do think there's 2 main solutions. The first one would be to actually recreate everything in JavaScript with all those modern tools, etc. We already have graphology that's been presented here by Guillaume 1 or 2 years ago. So it's a graph model, but it's mainly an API, so you can re-implement it while benefiting from all the plugins that have been already developed. So algorithms implementation mainly. Sigma's rendering engine in the new version that Guillaume's been working on is becoming faster and faster. So we already have some code. We might actually wrap it up and create something that works. And also it's working on the web with the web development spirit and tools. So this is something that I quite like. We could also go to the developing everything in C++ or Rust and compile it to bytecode and having a faster software. But this won't be a black box because we need actually APIs that will be able to communicate with JavaScript. And I think that's the main issue with this solution. Having a low-level code that will open APIs that will work with simple JavaScript without having to work only with low-level structures, I mean for plugins developers, could be painful, and I think it's better to actually not do this. Without these plugin constraints, I think the black box would have been something acceptable, but quite not. So our recommendation finally would be to actually embrace web culture, and if we want to develop Gephi for the web, not trying to do the browser as a virtual machine thing, but more developing something with JavaScript and all those tools. We have more solutions than we expected. Starting working with this talk, we actually didn't expect to say this at the end. Especially, you'll see the benchmarks, but the situation is not that bad for the WebGL implementation without having actually tried to do anything special for this talk. And I think developing Gephi for the web is something that would be totally possible. We have to rethink it with the capabilities of the web. And then we might be able to solve the actual same problems, which is our goal. So that's nice.
Thanks. So let's talk about the speed, right, on the web world. So we've done a benchmark, right? So I'm going to show a few charts, and they have the frames per second on the y-axis, and pay attention that it's log scales. So, right, it goes 10, 100, 1,000 frames per second, right? So here we test on different networks, 3 engines, the current Gephi engine in OpenGL, in orange. In blue, in the middle, we have the new OpenGL engine that has just been presented by Eduardo. And in gray, we have the WebGL engine in JavaScript. So basically, it's Sigma. We just did not try to display the labels in this benchmark. And it has been done on this same computer, which is a kind of researcher's computer. And these benchmarks have been done with the NVIDIA chip. But it's not a powerhouse, right? And the resolution is like 2,000 and a few hundreds by 1,400. So quite a big resolution. And as you can see, on these big networks, let's talk about the size of just the n. After the n, you have the number of nodes, and after the e, you have the number of edges. So this one, the Marvel Superheroes network, has 10,000 nodes and 100, almost 200,000 edges. And it's rendered quite comfortably with the new engines above 50 frames per second. And what you can see is that the JavaScript is already quite largely overperforming existing Gephi, right? So Sigma JS on the full screen resolution is much better. And the new OpenGL engine is also even a little better. And the new OpenGL engine allows to display huge graphs that we are not currently able to visualize in Gephi. Right, so like the Google graph, this one has 800,000 nodes and 5 million edges. So we have different options for the OpenGL, the new OpenGL engine. So we have Joggle and LWJGL, the 2 libraries, and we have different options in terms of when do you swap the buffers, do you wait for the full rendering, or do you give more reactivity to the users by allowing the buffers to swap at any moment? Whatever. These things produce kind of the same range of performance, so they don't matter so much for performance. We can pick whatever is good for us in terms of design and user experience, so it's just good to know. And now let's talk about scalability. So here it's different networks that have an increasingly large amount of nodes, so an order of magnitude each time, up to 10 million nodes. This network has no edge. And so first of all, you see that we have this kind of plateau in the beginning. This is just due to the fact that you have a cap in the number of frames per second. We don't see us human more than maybe 100 frames per second. So whether you cap it at 30 or 60 or whatever, actually all these engines could go much beyond. We just don't do it because it's useless. So the plateau here is not really representative. But then it starts to drop. And it starts to drop because there are too many nodes for the GPU, basically, or the CPU, depending. And what you can see first is that all of them start to drop at kind of the same moment, right, between 10,000 and 100,000 nodes. And then, so they don't drop necessarily at the same rate, but you can see that, for instance, we can reach 10 million nodes with the new OpenGL engine. Also, we couldn't load such huge networks with the WebGL engine. And so I must talk a little bit about that, because you've seen a lot the issues that arise with web technologies. So here, the file was too big, and we can actually find a turnaround to be able to load it. So we didn't take the time to develop that in addition to do this benchmark, because we didn't have the time. But basically, web technologies are not used to load huge files, and that's why it's break. So solutions exist. So we would be able to find turnarounds to load huge files. But currently, it's kind of not available, because that's not in the practices of these people. So we don't have the figures. So let's look at the edges now that we have seen for the nodes. And basically, it's kind of the same picture. So it drops at the same point. So it means first that in terms of scalability, one node and one edge are kind of worth the same, right? So you could estimate the size of your network in terms of nodes plus edges, right? And it gives you how far you would go. So basically, to have an idea, things are usable with your interactions with the software above 10 frames per second or around 10 frames per second and above. Below that, it becomes so laggy that you cannot really interact with the network. It works kind of a static thing, right? And you can see that we can almost go to 1 million edges with the new OpenGL engine, and we could also achieve quite decent performances with the WebGL. We also tried, though it looks like a stupid idea, to see what it looks like if we have networks with a huge amount of metadata. Let's say nodes have many attributes, like full text stuff or whatever. Well, it shouldn't change the rendering, right? And it doesn't change the rendering for the OpenGL engine. But it turns out that it actually takes a toll on the performance of the WebGL engine, even though the metadata doesn't matter to the rendering. And the reason is the crazy magic optimizations done by V8 are different with objects that have a lot of keys and a lot of stuff. So it makes different optimizations, and then the performance drops. So this would mean also this would lead us to develop a hybrid engine where we would split the rendering part and the metadata part, for instance, or such strategies. And let's talk about the screen resolution. On the left, you have on different networks the frames per second on a small screen, and on the right on a huge screen, that screen. And it's actually quite flat. It means that it depends much more on the size of your network than the size of your screen. And this is quite specific to OpenGL and WebGL. I think Canvas is not the same. So it means that we could have much bigger screens. Even on small chips, it will still work. And that's a really great news, including for the WebGL. So this is just the OpenGL, but it's also the case for WebGL. And let's look at the influence of a GPU, right? If you use a huge graphic card, so we've tried with the, on the right, the GeForce GTX 970, which scores like 8,000 on G3D Mark, while the left one scores only 1,300. And basically, WebGL in yellow and the new OpenGL engine in red gain performance, but current Gephi engine doesn't. So it seems to go down, but actually it's like 1 or 2 frames per second. Basically, you should just consider it's kind of the same. But the thing is, we have a CPU overhead, which caps the gain we have with a huge GPU. So we would gain more performance in the future. So let me wrap up that very quickly. If you're a developer, the takeaways here are that web technologies, we think, are the new multi-platform for graph visualization. WebGL allows you to visualize 10 to 100,000 of nodes plus edges on your browser today with a normal computer with no special graphic card. So this is great news. But the challenges are different. I will not dig into that again, but you've seen that. And we just have a few things to know if we go that way, which is that the libraries are not mature for data science. So we have to develop stuff in JavaScript that is more compliant with data science practices, and this will come. And these practices are not in the web culture, as you've seen. And also for plugins development and stuff like that, the researchers or the users would have to learn a new culture that is different from the Java world. And if you're a Gephi user, know that we will transition from a software to a project with maybe different tools, and that the web will be part of the future of Gephi. But this doesn't mean that we will drop the Java Gephi, and especially not in the moment. But if things go even worse with Oracle and stuff like that, and they really want to, I don't know, for instance, completely stop the OpenGL support or whatever I know, we have a fallback, which will be the web technologies. But right now, we don't plan to drop Java, and this might finally lead us to get a decent user experience for Gephi. Thank you very much for your attention. Yeah. In JavaScript? Okay, so does the running of the Force Atlas impact the performances for the rendering? And I think that considering that the rendering is almost only on the GPU in the ideal world, which means with the new engine, and the Force Atlas is only on the CPU, so we wouldn't lose too much of the performance, right? Yeah. So do we plan to use clustering algorithms to only show the edges that are relevant to the analysis and not all of them because it's too much? And the answer, I will want to say joker here. So this is a methodological question. There is no problem for implementing these such algorithms, right? But because we are so few of us, we focus more on the basics of Gephi, like the core engine and stuff like that. And this can be done as a plugin. And like, for instance, the Leiden algorithm that is a kind of another version of the Louvain algorithm for modularity clustering. The guys who published the paper, with the help of Eduardo, just published a plugin for Gephi, and this is the right path. So if these things comes, we will create the plugins, host them, and we might even include them in Gephi. And the same applies to the JavaScript world, where graphology is an engine that can host this kind of algorithms. And it's also possible to make a pull request in that direction. Another question, maybe? Did we consider WebGL frameworks like Three.js? Maybe this is a question for you.
Yes, at the beginning we thought about it, but the thing is, it brings us far from the metal, as Guillaume says. So basically it brings like 1 megabyte JavaScript just to draw disks and lines, which seems overkill. We prefer to go trying to actually work with WebGL directly, especially since we have only 2D needs. And there's no, except for Pixie.js, which is actually something we can think about, most WebGL engines are more 3D oriented. Which one? Regal. Okay. I'll take a look at it.
Are we?
It's really quick.
Quick, let's go.
That's right. Okay. It goes a little bit in the other direction, like not only viewing a subset, but also annotating it and helping to annotate. Think about show all the classes of the Unix kernel, but then I'm only interested in some parts, like I zoom in that part and make annotation by even by machine or by hand, and I'm missing it. Is it?
So this is an excellent question. I would just say that doing this kind of stuff is a UX issue, so we will be able to address this kind of issues in the web world and not in the Java world because it's so costly right now to develop advanced UX stuff in Java.
Is there something interesting?
It is something interesting, I think. We already have a few initiatives in that, and we can discuss about that later.
Cool.
Thank you very much.